Thank you, Paul, for insightful history of HPC. I really appreciate it. Yeah, my name is Sejt Korč. I'm a technical program manager for the private sector program at NCSA. I'm also associate adjunct professor at the Mechanical Science Engineering Department at the University of Illinois. My pleasure to be here. I understand, I'm the first one on the menu, and I was reading the other day, the research showed that people attention, goes down pretty much to zero after 3-4 hours, so kind of, privileged to be first one, You guys probably going to be watching what I was doing. So I'll start with the quote from Professor Tom Hughes. You guys might know him, he's a pretty big name in computational mechanics. So this was the view from 2003. And I was a young grad student at that time, so I was attending that conference, and I was puzzled what he said, even when supercomputers become a size of the football field, there will be still problems in engineering, that cannot be solved. And nowadays, when these laptops are probably, as powerful as supercomputers in late 90s or middle 90s, is it really, have we solved all the problems in engineering, or we have more? And I can say we have many more, when it comes to DNS, for example, approach in computational fluid dynamics or FEA, if you are talking about assemblies of modeling every single thing there, we are just scratching the surface even with petascale systems. And just to say more about that, this is Dr. Yon Hu from Rolls-Royce. He's one of our industrial partners, and this was for my C14. So he said, that in order to do the high fidelity virtual engine simulation in design of his products, he would probably need 1 trillion degrees of freedom. Well, when I say degrees of freedom, that means equations. So 1 trillion equations has to be solved. And he's thinking, it'll probably takes 1 billion core hours per calculation, So it's really, good old Tom Hughes, he was right, because now we have supercomputers of the size of the football field, and Blue Words is one of them. But we are still, far away from solving these problems. Now I'm going to put my marketing hat just briefly. So who we are the private sector program at NCSA. We pretty much solve industry's most demanding HPC challenges, and our partners are spanning from aerospace, agricultural, manufacturing, life sciences, you name it. And we like to say we are the largest HPC industrial engagement in the US, but we are probably in the world too. I know if Michael from Stuttgart is here, he might disagree with me, but I think we are at least one of the largest one in the world, when it comes to industrial collaborations on HPC level. So here's the data center opened in 2008, I believe, just for Blue Waters. It's 88,000 square feet. We are supplying 25 megawatts of electrical power there. Right now, we are using probably about maybe 50-40% of that, so lots of space for expansion. Our networking people originally have 100 gigabits per second connection. Now we are working on 400 gigabits per second there. So when it comes to hosting systems for industry, we have low-cost power and cooling. We have all the necessary help desk there, staffed all the time, and we are 1 block from the University Research Park. If you know University of Illinois, we have what we like to say Silicon Valley of Midwest, and lots of spin-off companies are there, so they like to be close to us actually when it comes to HPC computing. They can really transfer data very quickly. Here's the list of our partners. As I mentioned, it's manufacturing, technology, energy, and other things, and we were known actually to work a lot with manufacturing, but lately, we are working a lot with energy and other sectors. Now let's talk about NCSA supercomputers that we have on the floor in that building that I show you. So iForge is a supercomputer for industry. We don't piggyback anymore to NSF machines. We have our own dedicated resource just for industry. there are no academic uses there, you know, and what we like to say, it's 99% of the time actually up. One of the reasons is we have very resilient GPFS-based IBM file system, you know, it's really doing very good job there. So we are doing on-demand reservation, and we are hosting also, you know, we have hosted options there, you know, and what is important with iForge, it's an evergreen system. So every year we go through the update. We are always on the cutting edge with the chips. Right now we are Ivy Bridge. We are already experimenting with Haswell, you know, so a few months from now it's going to be Haswell. Blue Waters, of course, everybody knows about Blue Waters. You know, it's the largest NSF system, one of the biggest one in the world. We like to say we have 1 petaflop sustained performance with real applications, so unlike HPL, you know, we have achieved 1 petaflop with few of the real applications. It has featuring 400,000 cores, 12 million CUDA cores, 1.5 petabytes of RAM, and lots of storage, you know, about half exascale of the storage there. Here's the iForge, you know, zoom in. You can see what I was talking about. It's about 3,000 cores right now, mostly Ivy Bridge. We have also a part with under AMD, Abu Dhabi. These two nodes called Xeon E7, they have as much as 1.5 terabytes of memory, you know, so you can think about really SMP systems now, size of Altix, you know, a few years ago, also there. And here's the Blue Waters. As I mentioned, you know, very, very big system, size of the football field. What distinguishes, of course, Cray system is, you know, they have a Gemini interconnect, and that interconnect you will see in my next slides is really makes difference, you know, compared to other system, you know. So when it comes to engineering applications, you know, it's really important to have a good interconnection if you are really scaling very wide. So here's a for example. This is from iForge. This is the only one from iForge that I have in this presentation because focus is on Blue Waters. But you can see, you know, as we switched from Sandy Bridge to Ivy Bridge, for example, typical finite element application, most popular is Abacus, going from small system, small, relatively small, 5 million degrees of freedom, and one bigger one, 4 million degrees of freedom. You can see how much boost we get switching from Ivy Bridge to, from Sandy Bridge to Ivy Bridge, you know. That was really significant. Now I'm going to be talking about these actually breakthrough stories on Blue Waters, you know. So first one is 15,000 cores with LS-DYNA. It's LSTC product, explicit finite element. Then 20,000 cores with Fluent. Fluent is the most popular CFD code. And then 60,000 cores with WSMP. That's a sparse matrix solver library, direct solver library from IBM Watson. And of course, the biggest one is 100,000 cores with Alia multi-physics code, you know, probably the world record right now for engineering applications. And I'll be talking about OpenACC with GPUs because I understand, you know, this session is about accelerators, you know, so I have things there. So quickly, LS-DYNA, we started 2013. That was started with Rolls-Royce, who brought some of these big problems to Blue Waters, you know, and Cray was with us, and LSTC, the developers, you know, and we ported LSTC, LS-DYNA to Blue Waters, and you can see, and that time last year, you know, we scaled to 8,000 cores, and you can see also iForge having faster chips is actually faster on a lower scale up to maybe 1,500 cores, but then you can see that Blue Waters actually is taking over, you know, and scaling more. So why is that? As I mentioned, you know, the communication becomes very important when it comes to scaling of engineering applications. So you can see on a smaller scale, if you profile things like LS-DYNA, you can see that computation is primary thing, you know. But as you scale wider, communication become more important. As you go wider, even thousands of cores, you know, communication becomes very important. So really having a powerful network between the nodes is very important, you know, for engineering applications. So and this year we pushed LS-DYNA further. Now, you know, after this initial success, you know, many companies came to us, you know, and says, yeah, we are doing LS-DYNA too. Can you do stuff for us to, you know, try to benchmark and see where we go? So among them, Procter & Gamble, actually, they brought the largest problem size that could fit on Blue Waters, and it's featuring, of course, this is not a standard benchmark from ISV. This is actually a real-world problem that Procter & Gamble has. It's featuring real geometry, boundary conditions, and they have very difficult eroding contact conditions. We use the same MPP Dyna port. We were just tweaking a little bit more for this particular problem with, that P&G has. And you can see, now it was March 2014. This year, we actually broke this new record on 15,000 cores, So you can see, it was scaling pretty well up to 15,000 cores. You can see the solver itself was scaling well, but also the overall computational time was also scaling well, and went from 22 hours, to actually a little more than 4.5 hours, actually, on 15,000 cores. So just to put it in perspective, graph is good, but what that means, if we would run this on a serial computer, it'll takes more than a year, 400 days, and then we are down to 4.3 hours, actually, on 15,000 cores. So this was the world record at the time for engineering commercial application, But then, so briefly now, this kind of collaboration is very essential, So that's us NCSA working with ISV, who actually knows the code best. We also work with our hardware provider, in this case, Cray, and of course, our industrial partners who are bringing real-world engineering problems. So this kind of collaboration really is, turned out to be very good. And so we were looking at different things, how far we can go, maybe, improve even more. So these are some of the issues. Maybe the most important one is improving the load balancing and that eroding contact, in rigid body algorithms, and that's what we are looking right now. You can see also the view of our 3D torus. You can see when I was running some of these jobs, you can see, the topological awareness is pretty good, but you can see, my job was this pinkish one, so you can see, there are some parts, we're still not next to each other, so we were going lots of traffic through the torus. So on the CFD side, people become jealous, says, okay, doing so much on FEA, but CFD is known to scale more. What can we do there? So Ansys came to us, Fluent developers, and they created a pretty big problem size of 830 million mesh elements. It was featuring fluid flow, energy, chemical species, and was cold, no combustion there. And according to Ansys, which this was one of the biggest real-world cases ever, so we created mesh, and creating mesh, actually we use that EX node that I showed you, Intel EX node with 1.5 terabytes of memory. Otherwise, we wouldn't be able to do that. Ansys couldn't do it, so we do it on iForge first. Then we brought the input files, to create to our Blue Waters, and then we were doing the benchmark. And you can see, in this case, we actually reached 20,000 cores, and it was the speed up was still pretty good on 20,000. More than 80% efficiency before it starts dropping. So Fluent is telling us this is the biggest scaling they have ever got. So this was about Fluent. Now. We are not working only with ISVs. We are actually working with the academic codes. And the most promising one in the engineering domain is the one from, at least that we touched, is the one from Barcelona Supercomputing Center. It's a multi-physics code. What is interesting with ALIA, or their code, is actually from the scratch, is being designed for very extreme scaling. So you can see some features there. It has unstructured spatial discretization. It has both explicit and implicit integration schemes. It has staggered schemes for the multi-physics, which scales better than just coupling or doing more of the full staggered scheme. They do actually, not me, mesh partitioning in hybrid parallel implementations, and solvers right now are mostly conjugate gradient solvers with preconditioning, and it's very easy to use that. I never used it before, so when I was porting this code to Blue Waters, I was really amazed, how modular is the code, with each module actually on the command line representing different physics. Paul, do you mind if I just take a sip? Too much coffee, I guess. So again, Alia has been ported to Blue Waters in March 2014, and once we reached that 100,000 course scaling, it was pretty much all over the net. HPC was talking about this, and it's been nominated for the top supercomputing achievement. That's what I heard. So maybe I'll appreciate your vote, guys. If you go there anytime to HPC via Reader's Choice. So let's talk what we have done. Again, we never work with the standard benchmark. We work with the real-world problems. So my amigos from Spain, they brought two problems. One was a human heart. So we have a coupled electrical propagation with solid mechanics there. Mechanical response has features 3.4 billion elements, and it's scaled to 100,000 cores. The other one is a pure CFD. It's flow in a kiln furnace, featuring transient incompressible turbulent flow with LES coupled with energy in combustion. We have combustion here. We were modeling 6 species there. It also has a pretty big mesh, unstructured mesh, 4.22 billion elements. That one scaled to 100,000 cores again. And you can see the scaling, for example, for this second problem. You can see the scaling is very good. And even on 100,000 cores, you can see that we have achieved almost 90% efficiency. So now the logical question would be why we didn't go further, because we have 400,000 cores at Blue Waters. Well, they started actually twisting my arms. They said, you can't use the whole Blue Waters. We have PREX, we have NSF users, we have all of this, and you're doing from your Steph account, So you already use so many of SU. So I stopped at that time, and but it's on our do list, So when I get my own allocation, I'll really try to see, how far it can go. I can bet it can actually go to 500,000 cores, easily with this problem size. It's just to put it in perspective again. Graphs are great, but what this means. Now we are really talking about extreme things. If you run this with enough memory on a serial process, it will take 17.4 years. You're talking about, a kid being born and going all the way to the college. You're still running the same problem versus, less than 2 hours if we were actually able to see this, to solve this. One more thing. This slide actually didn't show up, so I don't know why, So I have to put my laptop here for this slide. So part of my research interests are direct sparse solvers. And this one is from Watson IBM, same guys who beat humans on Jeopardy. And this one is scaling better than any other direct solver in the world. When it comes to ill-conditioned problems that you see very often, either in CFD or in FEA, you have to actually do the direct factorization instead of doing iterative methods with conjugate gradient and preconditioning. It's not going to help you. You have to do the factorization. And what's the perspective there? So it turned out actually we were able to scale this one with 40 million degrees of freedom. It means 40 million unknowns, all the way to over 30,000 cores. We are trying now actually to 60,000 cores to see what's going to happen there. And the performances was pretty good on Blue Waters. We achieved 60 teraflops there. So when it comes to sparse linear algebra, everything is sparse. You're really 99% of zeros. You're really talking about these things which are not zeros. This kind of performance is really great. So okay, let's talk about GPUs now. I have only 6 minutes, but I think it's been enough. So this is the view from 2010, SC 2010. You can see people predicted there will be pretty significant shift going from 2012 to 2016, when in 2016 something else. With that something else, I'm pretty sure now it's going to be GPUs or Xeon Phi or new AMD, fused CPU, GPU solutions. are going to be dominant, actually. And I can't agree more. We really see this shift, happening, starting pretty much in 2011. So when it comes to GPU computing, you have pretty much three options right now. You can drop in acceleration with the libraries like CU BLAS or CU Sparse from NVIDIA, and you are good to go. Or you can go the other way around. On the right-hand side, you can do pretty much full CUDA programming. I have never been a fan of CUDA programming because it's not easy to learn. It also looks a little cryptic. So OpenACC, is kind of incremental accelerated applications. If you are an OpenMP programmer, you're going to like OpenACC. So again, OpenACC started in 2011 about SC time, and the pragmas, they look pretty much like OpenMP. So you can really do incrementally taking these kernels, to GPUs and then do the programming there. I think this was mentioned even on Friday night, so what is the menace here on GPU computing, this PCIe, which is order of magnitude slower right now than the access, for example, of GPU memory. And you can see, if you are shuffling this data to PCIe, you're going to be pretty much, very slow, probably much slower than CPU only. So I have been with NCSA for 16 years now, and when first GPU started in 2006, 2007, it was very promising. And then for a very long period of time, we would see single node, single precision, and that's it. The reason was actually because when it comes to scaling these things with MPI and also with accelerating within the node, you have to actually go through that PCI to reach the MPI, and then MPI do this stuff, and then of course going through that every time it's very expensive, so that's why we didn't see much of the movement in that front when it comes to multinodal acceleration until recently when vendor and community responded, and then we have first GPU aware MPI that is supported both on with NVIDIA GPU Direct and also with Cray MPitch RDMA enabled CUDA or GPU aware MPI, where GPU memory buffers to be passed directly to MPI function, and then eliminating the manually copying every time when you have to go actually to MPI. And then recently, what NVIDIA introduced is in CUDA 6, it's a unified virtual memory where it's kind of blended GPU and CPU into a single addressable space from the programmer's perspective, this is much easier. You don't have to even worry much about, where your data is anymore. Is it on CPU or device and things of that sort. I understand that colleagues from AMD are doing the similar things right now, with their solutions too. And this is great news. Okay, so here's an example now. This is a very important kernel. You can see pretty much on many engineering codes, and other science code, So this is a finite difference for the hyperbolic equation. In this case, it's a Laplace equation for the heat conduction. If you can do finite difference there, you can pretty much iteratively converge, until you get to some convergence criteria, and then pronounce, this is a solution. So we have an old code, which is actually a combination of MPI and OpenMP hybrid code. So in there, there is an exchange of this data on the boundaries. You see that these, if we do a simple domain decomposition, these things within the MPI, they have to exchange data on the boundaries. And in order to do that, you have to, of course, do that with MPI because these are different processes. And then remember, every time to do that, actually, for every iteration, for every domain, you have to go to PCIe, and that's pretty significant overhead that you get. So if you use this pragmas, ACC host data is actually that is telling the code to actually make the address of the device data available on the host right away. So when you do the scaling, you can see the CPU only code with MPI and OpenMP scaling pretty well. Scaling on 16 nodes, which is on our XC6 Craze 256 cores is scaling pretty well, 60 something, the speed up. But you can see, the combination of OpenACC with GPU-aware MPI is really making a huge difference. You can see we're scaling, about 3 times faster. And you can see also the difference between if you do the parallel construct, which is kind of easier way, you let the compiler, OpenACC compiler decides, or if you do a little bit harder way, with kernels construct, you can see, you can get more speed up actually with the parallel construct, where you are actually attacking every loop, just like OpenMP. If you do the profiling, you can see what's happening, so for the without host use device, without GPU-aware MPI, your time is pretty much very long for this problem size. You're spending shuffling this data to PCIe about 54 minutes. With host device, you can see, it's about 3.7 minutes of pure GPU computing. That's it. That's why we see that huge difference. This is my last slide. We are not the only ones who are doing this. For example, Simulia from Dassault, they with this Abacus code, they are providing pretty good multinodal GPU acceleration too. You can see, the comparison speed up between our XC6 that has CPUs only and XK7 that has attached GPU to every CPU, and you can see, we get about 1/3, faster, faster speed up, than CPU only. I think this would be my last slide. I can see the 0 here, so it means I was pretty much on time. Thank you.
I have one. So how much additional effort was it required to go from the non-GPU version to the GPU version?
As I said, the original code is MPI with OpenMP. So what we really did there, we replaced the OpenMP pragmas with OpenACC. And not everything is working right now. For example, we have to turn the 2D arrays to 1D array, which is supported right now with PGI compiler, with this CUDA-aware GPI. But it's not significant. It's not very significant. So we were able really, to do this. Yeah.
So, quick question. So all the scaling at the large end were on the CPUs, and so you're looking at 100,000 cores. To integrate into those codes, the accelerators, and account for all of the communication, how long, sort of a follow-up to Paul, how long do you think it'll be before this GPUs will actually start seeing that kind of same scaling that you're getting out at the extreme levels?
So if you're talking about Alia, of course, we don't have access to ISV codes. They have source but for Alia, for our collaboration with Barcelona Supercomputing Center, the code itself is a hybrid MPI OpenMP. So we are thinking about actually doing that exactly. We are thinking about replacing OpenMP pragmas with OpenACC and see what's going to happen there. Of course, we won't be able to go to 100,000 cores because we don't have 100,000 cores on the GPU side, but we'll see what's going to happen on a scale that we can go with XK7 part of the Blue Waters.
Another question. It's kind of a variation of what Jack was asking, but can you give us any sense of, having all these accelerators, about how much of the work that gets done at NCSA with industrial partners that uses this is experimental or exploratory, just trying to see what they can do, versus actual production engineering work or production research?
For GPUs only?
Yeah, that it's involving GPUs or fire, anything.
The production part with GPUs is close to 0 right now. Everybody, when it comes to industry, there is always lag. And that lag is, I don't know, 5-10 years maybe. So really, they are right now very actively looking what we are doing. They are coming to us and asking, hey, if I run Fluent on GPUs, if I run Abacus on GPU, how much performance gain I'm getting? Is it worth for me actually to get GPUs? Is it worth for me actually to run on your GPUs. And the other thing is actually when it comes to ISVs, they can also benefit from the licensing scheme with GPUs because most of the ISVs don't charge extra for GPU acceleration. So it's right now it's under their very close watch right now, I would say. Yeah.
Yeah. On the multi-physics applications, for each physics part, I know for the BSc application, you mentioned there were modules and so on. My question revolves around if for the multi-physics applications, are there different image files for each multi-physics that you launch, or is it just one big one like you would do with MPI and so on?
It's a one big one, but on a command line, I'm actually calling different modules and combining them. And remember that the scheme is staggered, so every step, for example, of fluid flow, then is followed by heat transfer, then fluid flow and heat transfer. So that's how it works. Of course, I'm not a developer. So.
Thank you very much.
Thank you.